Hello kids. Today we're going to discuss a different topic. It's rather a confusing topic for most of the kids who are not able to distinguish between center of mass and center of gravity. We will be also looking this into the perspective of equilibrium, how an object attains equilibrium, and what is the role of center of mass in maintaining that equilibrium, right? So let's get into it. Center of mass. Uh, when we talk about geometrical objects in mathematics or in daily life, we understand that they are supposed to have a center, right? Center where we can say that the whole mass of the object can be balanced, right? Now that in mathematics we call as a centroid, right? Let's say if it's a circle, then the center of the circle is going to be the centroid, right? If it's a sphere, again, the center is going to be the centroid. That's the point where the whole mass is, respectively balanced at that single point, right? So, what we can say that to find center of mass, we take out this irregular shape, right? And we're going to put it we're going to hang this from this point, green point, right over here, and we're just going to put a plumb line along it. Wherever this is hanging, I mean it's freely hanging, so if it's pointed downward due to gravity, from this pivot, and the plumb line gives us this traceable line, so we're going to trace this plumb line on this irregular shape of paper. Now we're going to take another point and make it as a pivot and hang it again and let it float wherever it stops, and we're going to put another plumb line and trace the other line. Wherever these two lines are now going to intersect, we're going to say that that's the center of mass, right? This is a very simple method of finding a center of mass. So let's look at this diagram to the left. We see that we have a geometrical symmetry, right? These two objects, this dumbbell looks to be the same, right? It's symmetrical, but if you can see, it's 100 pounds on the left and 500 pounds on the right. That means on the right the mass is a lot more than on the left, while the geometric center is supposed to be this middle point, right? As per the diagram, if you don't count the mass, we just look at this geometrical object, we say that this point is a geometric center, but uh, the center of mass is actually going to be towards this point, right, where the red pointer is. Why? Because this is much larger mass at this point, and there's just 100 pounds on this side, so the mass is going to be more towards this side. If I want to lift this up, then I need to approach this point rather than the geometric center, and if I try to lift it up using the geometric center, it is going to topple, right? So to maintain a balance while lifting this dumbbell, I need to account for this center of mass, wherever the whole mass of the body will be acting, and I can simply balance it on just a pin, right? That's what center of mass is supposed to be, right? To further understand what center of mass is going to be, we're going to look into this brief animation where we're going to say that a center of mass is a point where if a linear force, right, a linear force acts, the object must only have linear acceleration, right, and no torque. That means we are not going to expect any moment either in the clockwise or in the anti-clockwise direction. So the force must only create a linear motion in the object, right? So let's say if we have an object, we apply force. Now remember, this blue line in the middle is actually representing this blue line in the middle is representing the center of mass, right, where the center of mass is going to be, right? Let's say this is the 100 pounds, this is a 500 pound dumbbell. Is the same one, but I did not make it in the geometric symmetry, so don't mind if it looks a bit different. I'm just trying to simulate the mass, right? Now if I am going to apply a force on the center of mass, right, it's a little higher, but let's suppose if it's on the center of mass, the object is supposed to move in a linear fashion, right? No rotation whatsoever is supposed to be there, no moment created by this force. But if I apply a force uh, other than the center of mass, there's supposed to be rotation, right? And whichever side it is on, the force is farther away, it is going to create a torque in that direction, right? In this case, in the second case, where we see that the force is above the center of mass line, so we're going to have a torque from the top side, which is the clockwise direction. But if we have the object and we apply the force at the lower end, right, then we see anti-clockwise or counterclockwise torque. So this is the effect of center of mass, right? So to balance the force, the action of a force in a linear fashion, we need to understand that a free body, now this is a free body, we're not accounting for the gravity at this moment, it is just a free body. We're trying to simulate the effect of center of mass, right? And what a force is going to do with it. If it's on the center of mass, there is going to be no rotation. When it's other than the center of mass, it is going to create torque, right? Like just like in case 2 and case 3. Moving on, now we're going to look into the next idea, which is the center of gravity. Now I would definitely call this just like the center of mass, but now we're going to understand that when we use the word gravity, we are referring to a quantity which is actually vectorial in understanding, right? Now over here, when we talk about center of mass, we need to understand that mass is a base quantity, and it is a scalar quantity, right? It is not represented by a vector. While in the case of gravity, we talk about gravitation acceleration. So acceleration is a vector quantity, right? So vector quantities are represented by vector, and in case of gravity, which is always downward, in the positive direction, it is supposed to be downward towards the center of the earth. So we're going to consider that the center of gravity for any object is supposed to be pointed downwards from its center of mass. For this disk, we are considering the center of mass as a center of gravity, while depicting it as an arrow, right? So now let's distinguish between centroid and center of gravity, right? Now what is centroid? Is it is the center of mass, right? It's a mathematical name for center of mass, right? Now the centroid of a plane figure is the arithmetic mean position of all the points in the figure, and formally it is the point at which a cutout of the shape could be perfectly balanced on the tip of a pin, right? So you can balance it, that single object at that point, right? That is the center of mass, or the centroid. Now what is center of gravity? Center of gravity of a material body is a point that may be used for a summary description of gravitational interactions, right? Now this is the point where the gravity is going to interact. Now as you can see, on this balance, we see the right side is heavier than the left one, right? There's more mass, and we see a disbalance. Even though this is a disbalance, it is still perfectly balanced, right? And at that point, we call that as a center of gravity. Where we are balancing it, right? The point at the base, right? That is the center of gravity. Why? Because at that point, this wedge or a pin, if we're balancing on a pin, the pointer is actually stopping the base of this whole balance to hold up and to stay in this rest condition. So that point is going to be the center of gravity, right? So now we are going to consider that center of gravity is the point which is the balancing point as well, right? We can balance an object if we line up the center of mass and the center of gravity, and we understand that there is no net torque being generated, right? So this refers to the stability of an object to be in a certain condition of rest or motion, right? For example, Earth is in a constant motion, both in spin and in linear way, right? It's in a circular motion, right? So when we talk about such objects which are perpetually in motion, then we are going to understand that no net torque is going to generate any angular velocity or acceleration additional to what already is there, right, in terms of um, angular motion, right? And in terms of rest, the object is not supposed to move about or turn about, right? That's what we call as stability of an object. It will retain its initial condition of either uniform motion or rest. So now let's look into the idea of this stability. We use a term known as equilibrium. Now equilibrium is a state in which the object, if disturbed, it will try to revert back to its original condition, which may be of rest or uniform motion, right? Now, when do we say we have attained equilibrium? When there is no net force or no net torque acting on a body, right? Now, let's look at this example. We have these two squares upon which four forces are acting, right? Now we have two forces in the vertical direction, right? One upward, which is 50 newtons, and the other one is downward, that is also 50 newtons. And we see that both of them are in the same line of action, so they will cancel each other's effect, so there will be no net vertical movement, right? Now in the horizontal direction, we have 30 newtons to the left and 30 newtons to the right. So again, these are balanced and they have the same line of action, so they will cancel each other's effect and they will not create any rotational effect, and there will be no net force in this condition on the box. So the box is either going to retain its rest position, which it appears to be at rest, so it will retain its rest condition, and that's when we say this is an equilibrium, right? Now let's take another example. If we increase the force to the x-axis, right, on the horizontal axis, we see that now we have 75 Newton on both sides. Still they will cancel out each other since they're equal, so there will be no net force acting on this object, hence no acceleration, no change in the state of rest or uniform motion, hence this is an equilibrium. That could be said for many cases, just like this one and the second one, where we have 15 Newton forces applied at 120 degrees angles to a central point. So if an object is pulled in these three directions, right, there will be no net movement. Why? Because the net sum of these forces will be neutralized, right? So now let's look into the rotational effect, because we're saying that equilibrium is a state where there is no net force or net torque, right? So let's look into the torque, which I'm going to now divide equilibrium into two separate conditions. One, we are going to define it using the forces, we just did that, and the second, we're going to use torque to define the condition of an equilibrium of an object, right? Now let's look at the case of this two kids balanced on this wedge, right? Now if you look at it, these two boys, if the boy and the girl, if they're balanced, we see there is going to be no net torque in any of the direction. If either one were heavier, then that side would be lowered and the other side would be raised, so then we can say there wasn't some net torque, right? So to balance an object, this point P is the pivot, right? And this weight is going to create this clockwise direction torque, and the girl's weight is going to create a counterclockwise torque. So if it is balanced, then we're going to say that these two torques are equal and they will cancel out each other's effect, and hence there will be no net torque on the object. So we're going to consider that these two conditions once met, we can say that an object is truly in the state of equilibrium, right? So for any object, let's say if you have a question to answer, any question that refers to the conditions of an equilibrium of an object, you need to understand that you have to explain both these conditions. Until unless both these conditions are satisfied, we are not going to say that the object is in equilibrium, right? We need to consider that both these conditions need to be satisfied, right? Now in contrast to the conditions of equilibrium, we have three states of equilibrium as well, right? Now, by state, we mean that the initial state in which the object really was, right? And while discussing center of gravity, we raised this point that it refers to the stability and the equilibrium as well. Now, we're going to put center of gravity into effect, how it really affects the equilibrium, and how we can help stabilize certain objects, right? So, when we talk about the states of equilibrium, there are three states. One is the stable, in which, let's take an example of this cone. If we put the cone with the pointer towards the top, we are going to see that the center of mass or the center of gravity is actually quite close to the ground, and if you try to apply a certain torque to try to topple this down, it will try to revert back to its original position, and that would be quite easy for it. It will revert back easily. But if we take the case of the second cone, which is inverted, uh, even a little force or torque is going to topple this, and the center of gravity will no longer be in its initial state, right? If it's at a higher location right now, once we topple this, it would be in a lower location, right? It would be reduced the height from the ground, so that's when we say it's unstable equilibrium state, right? Even if you try to balance it somehow, uh, once we create an imbalance, it will immediately return to a different state, and it will not be able to return back to its original standing position, right? Now, the third case is quite different from these two, in which the center of gravity will retain its height even under the action of a force or a torque, right? Now, consider the case of a ball. If I spin it or roll it, either way, it will move forward in a linear fashion while it's spinning, right? Nonetheless, its center of gravity will retain, and as I said, right, it will retain its height from the ground, and that's when we say that even if the object is disturbed, it will retain its neutral position of center of gravity, even during the motion, or even after the effect of force, right? So in this case, we are going to say that the object is in a neutral equilibrium, right? Now, these are the three states of equilibrium, right? Do not confuse them with the conditions. Conditions are when there's going to be net sum going to be zero for forces and torques, while in states of equilibrium, we discuss it when we're trying to create a disturbance in the system, right? That's when we're going to discuss the states. So in terms of forces and torques, we discuss conditions, and in terms of inducing a change to this condition of equilibrium, right? We're going to call that we're going to discuss the states of equilibrium to express our answers, right? Now, let's get into a unique case of stability, right? Where we're going to discuss the center of mass having its uh, effect on the stability of a vehicle, when we're going to have a system of objects, right? When we have a system of masses rather than just one fixed mass in our previous cases, unlike before. These were fixed objects, right? Two different masses, but it was a fixed assembly. In this case, when we look at this truck, we see that it is loaded with tree logs. So the tree logs are free to move around, right? They're not going to follow of themselves, but since they are a bit loosened up, so they will move about, and they will have their own center of mass, which will come into effect in discussing the stability of this truck, whether it's going to topple or at higher turns, right? If it's a heighted road or a tilted road, whether the truck is going to topple or not, that depends on how high the center of mass is, right? We just discussed that the height of the center of gravity defines the stability of a vehicle, and we do know that the center of gravity is considered from center of mass. We just need to put an arrowhead from the center of mass straight down towards the ground, and that's where we're going to say that the weight of the object is acting. And if the center of mass of different masses in an assembly, in this case we have the truck, which has its own center of mass in the bottom right here, and the load, which is the tree log, is going to have its center of mass in the higher. So combined, we can say the center of mass is going to be somewhere here while it's in this position, and it's a bit stable. Why? Because it's closer to the ground. But if we overload this tree log, right, then what's going to happen? That the load center of mass is now much higher. As a result, the combined center of mass of the truck as well as this tree load is going to be now higher than the previous state. So on a tilted road, that may pose some risk of toppling the truck, and we usually get to see such accidents on highways when there are sharp turns and there are tilted roads. You would find that the trucks that are overloaded, or they're not counting the effect of the center of mass, then it's going to be a toppling accident, right? The truck may topple, that and it may cause some risks on the road. So we need to understand, when we're discussing the system of masses, things are a little different. We need to draw the center of masses of all different parts of the assembly. Each mass is supposed to have its own center of mass, and we then try to evaluate the combined center of mass where it is supposed to be, right? And then we're going to discuss the height of that center of mass from the ground and discussing the stability of a vehicle, right? So to make any vehicle stabilize, we need to ensure that the center of mass is much closer to the ground, so that the vehicle at high speeds, or in this case high loading, is going to be very much stable, right? I hope I'm able to clarify some of the confusions in this topic. I know these are two terms which we use frequently. Just distinguish center of mass and center of gravity using vector and scalar understanding. There is nothing else peculiar about these two. There are most of the cases that we discuss both of them simultaneously, or nonetheless individually. We are not going to confuse them, just because one is a scalar quantity and the other is a vector quantity. Other than that, it's the same point on the object, so don't get confused. It's the same point on the object. One is just represented as a vector, the other we just discuss as a perspective of a scalar magnitude of mass, right? Thank you for your time.